Thanks a lot, everyone. So just to make it extra clear and or confusing, I'm Dave, and he's David, and we build JavaScript JITs. And our dream in doing all this stuff is to run JavaScript as fast as C. So sure, that is pretty much totally crazy, but it turns out that current systems actually are getting pretty close, and there definitely will be lots of assembly on slides today as we show you the native code that does this. So just a little bit of background, really what sort of makes this hard, right? If you use a compiler, that generally helps make your code run fast by compiling to native code. So the thing that makes it hard for JavaScript is the fact that JavaScript is untyped. You don't have any type declarations or anything. And the reason is that having different types in the program means the processor needs to do different things. So in JavaScript, A plus B can actually do a lot of different things, right? If you're adding strings or if you're adding numbers, that's going to require different native code. Same thing for properties. If you look at these two things here, if we try to access this color property on a string or an object, you actually have to do different things, so you need different code. And in JS, it turns out to get even more complicated. So in here, I just added something where I'm adding a couple of floating point numbers. As an optimization, the engine often tries to do things with integers, but you might need floats. And so even though they're the same JS type, you actually need different JIT code for even those two things. And it's also the same here. For these two objects on the bottom, they both have a color property. It both has the same value. But in most JITs, you'll actually need to run a little bit different code to make that happen. So today we're going to talk about two different kinds of JITs here. So first, there's the simpler untyped JIT. And the idea of that one is for every little piece of your JavaScript program, you generate some native code that handles all possible types. So it's like you drop down this little multi-tool that can do everything for every statement in your program. And the good thing about that is it's fairly simple to do, and the generated code can run no matter what types your program actually has. But the code is pretty big because you're generating a lot of code. Maybe some of it won't even run, and it's a little bit hard to optimize. So that one actually turns out to give you pretty fast code. But if you want to get even better, what you can do is use what we call the type JIT. So in this one, either by using some type inference or just measuring dynamically, you try to guess types for each variable, and then you generate code specialized for those types. So in this case, for each statement in the program, you try to figure out what the types are, use a little bit of specialized code just for that, so you get sort of smaller code, and it's more optimized. The disadvantage is that you do have to recompile if types change, right? So if you were sort of guessed there would be a nail, so you used a hammer in your compiler, and it turns out there's a screw, that's not really going to work. You need to do something else. So now on to the assembly, and David's going to start out by telling us about math. This isn't your first slide, is it? There you go.
Yeah.
Sorry about that.
So to start off, let's take this sample function here. It takes in a left and right variable and just adds them. And let's see how this would work in an untyped compiler. So an untyped compiler wants to handle everything. So we want to generate code that'll handle all possible types for left and right. But we want to start somewhere simple. So let's start off with just assuming that left and right are going to be numbers. And as you know, JavaScript semantics say that JavaScript numbers are always floating point. But machines can use both integers and floats. And integers tend to be faster. So if we call this function with, say, 5 and 10, we want to treat those as integers instead of floats. So let's start off. Let's say our compiler has a register allocator, and it decides that the left and right-hand side should be in registers EAX and EDX. We might generate just this one instruction, machine instruction, that says add the two integers in registers EDX and EAX. But let's say EAX is actually a pointer to a string, and EDX is number 35. So this is bad because we'll just be adding a number to a string, which is, a number to a pointer to memory, which is completely bogus, and at best it's some kind of security risk. So we can't do that. So what we need to do is insert type checks before the add, and that's this code in magenta here. And now the compiler needs to keep track of both the types and the values of the variables. So let's see what would happen when we run this code. Let's say we're adding numbers 27 and 35. The first thing we'll do is check to see if the left-hand's type in register EDI is 32-bit integer, and it is. So that check passes. Next, we'll check the right-hand side's type in the EBX register, and it is an integer, so that passes. And now we can just take the values in EAX 27, EDX 35, add them, and we get our result, which is 62. So does this always work? Well, let's see. What if we call f with a huge number? So this is the maximum signed integer that can be represented on a 32-bit machine. And this time, if we add them, the machine is not going to have enough bits to represent the actual result, so it'll just overflow and get -2. So let's see what's supposed to happen in JavaScript when we add these two numbers. We actually get 4 billion. And is 4 billion equal to -2? No. So we have to do something there. And luckily, the machine sets an overflow bit on the CPU whenever an overflow occurs. So we can just check that bit. And when it happens, do floating point math instead. So what about floats? Let's say we pass f 2.7 and pi, and we want that to be fast too. So in this case, we can extend each of these little type checks with another block of code that will try to coerce the two inputs to floating point numbers. And if those pass and it can get floats out of them, it will add them together and continue running JIT code. As you can see, this compiling this whole add expression for numbers is about 30 instructions. So let's write a little benchmark. Let's say we have a 2D game, and we say we want to compute the distance between this lady and the cow. We might use Euclidean distance or something. So this is a small benchmark that loops over two variables and just computes the distance between them. And in an untyped compiler, each of those little sub-expressions would be compiled separately. And in the end, we'd get about 230 instructions for the entirety of the loop. And that seems like a lot, but despite that, JagerMonkey, the untyped compiler in Firefox, can run 100 million iterations of that in 1 second, which is pretty cool for JavaScript. It means in 1 second, you can do 100 million operations. But can we do better? So let's say we had a typed compiler, and the typed compiler can just, maybe it wants to assume that every value in this function is going to be an integer. And then we can start making observations, like this a minus I times a minus I will never change inside the innermost loop. So we can actually pull it out into the outer loop. And this is called hoisting. And why couldn't we do that in an untyped JIT? Well, let's say we had this crazy object with a value of hook, and every time the value of function is called, it increases this global variable called ham. If you were to pass this object into our benchmark, JavaScript semantics say that ham has to be increased every time the object is used in one of those arithmetic expressions. So the hoisting is only valid if we've proved or assumed that every variable in the function is an integer. Then we can make another observation in b minus j times b minus j. We don't have to compute b minus j twice, so we can just store that in a temporary variable, and that's called redundancy elimination. So in a typed JIT, this is a sample of assembly from Mozilla's in-development typed JIT called IronMonkey. It's not the full assembly. I've removed some crappy register allocation instructions. So we'll get to this eventually. But as you can see, there's just a subtraction, a multiplication, and an addition. We still have our overflow checks. And on the multiplication, there's also this test instruction. And that's testing for 0, because in JavaScript, if you have, say, -1 times 0, that actually has to yield -0, which can't be represented in an integer. So we have to check for that. And IronMonkey runs this in 250 milliseconds, so that's 4x faster than the untyped JIT. But if it was a little smarter, it could recognize that if you have an expression a times a, it'll never be negative. So we could get this down to 6 instructions. And that runs in just 220 milliseconds, or 4.5 times faster than the untyped JIT. So our goal is to get as fast as C. How close do we get to that? So in C, this is just 4 instructions, really 3, our subtraction, multiplication, add, and then a register move. And C runs this in 97 milliseconds. So an untyped JIT got within 10x of C, and a type JIT gets within 2 or 3x of C. That's actually really cool, considering that 3 or 4 years ago, JavaScript was 100x slower than C. But how can we do better? Well, in this case, it's actually pretty hard. There's this semantic gap, where JavaScript just does not have integers. It only has floats. And C has integers, so it does not need those overflow checks. And now Dave is going to talk about property access.
Okay, so this is the other major type of JIT code that we're going to show you, is how objects and object properties work. And in general, this is one of the most important optimizations in practice. It gives a huge speed up. It's important for real programs. And so I'm going to, because it's complicated, right? JS objects and properties are complicated, and the JIT code gets complicated too. I boiled this down to pretty much the simplest thing I could possibly think of, just evaluating one little expression, node.next. It's just to get a property. And I'm thinking of kind of a linked list here that I can traverse. So I did that so I could sort of do some benchmarks and show the performance. So in order to show you how you JIT these things, first I have to show you what's inside a JS object. So here's the constructor I have in mind. And this is from SpiderMonkey, a simplified version of how that object's represented. It's just this little memory object, a C struct. So there's some stuff in there like the prototype and things you would expect. But the most important things there are, first there's the shape. And that's something that gives the object format. So the main things it has are a list of properties, and then a slot index as to where you can actually find each one. And the thing to note about these is they're generally shared. So if you have, what the system will try to do is every object that looks like this, it'll try to make sure it gets the same shape and has shape 45, so you can easily tell that it does. And then the other major thing is the slots. And that's just where the values are held. It's just in a little array of JavaScript values. And so to look up the next property, what you do if you're not using a JIT is first you go to this shape table, you find next, you see, okay, that's in slot 1. And then you go over to the slot array and you read slot 1. And you say, okay, that has type special and the value is null. So let's try to JIT this in an untyped JIT like JagerMonkey. So we'll just start off. First thing we'll do is load up the type tag and verify that it's an object. It's just like before. We have some fast path for object. We need to make sure we have that. So we're just loading a tag from memory. We compare to this FF87, which tells us it's an object. So if that's good, then we continue on. Now we load the value. Note there is some little registry allocation glitch here. Fairly harmless, but these things do happen. And so now we have the object we want to operate. So what do we do next? Well, the untyped JIT actually has a problem here, right? For that one, we want to generate fast code that handles all the types. But here's the types you can get. You could get an object that has a type that looks like this. Here's a different type of object, requires different JIT code. Here's a different type of object, even more JIT code. So really, there's an infinite number of possible types here. So there's no way that you could generate them all. And worse than that, the JIT doesn't even know like what they are, what shapes they would have, how you'd identify them, anything at all. So pretty much at this point, we get to go to the simplicity and ease of self-modifying code. And so this is called inline caching. It's a bit of a historical term. It's from the self-research that really pioneered a lot of optimization for dynamic languages. And so to show you how that works, I'm going to work backwards. So first, I'm going to show you the code that we want to get. So this would be code that would run fast and get the next property for the shape 45. So we have that top that operates, that I already showed you, that gets the object. So the next thing we need to do is make sure that we have shape 45. So in this blue code here, ESI holds the object. So we're just loading that shape field. We test it, keep going if it matches. So then the next thing we do is we load that slots pointer out of the same object. And then at the bottom here, we load the type and value. So this ESI plus 12, that's loading from the slot array, the type, and then we load the value. So the only problem here is that these values in white, you don't know them at compile time. We don't know what the shape is, we don't know what shape to expect, or what the formats are. And the idea of inline caching is to really say, well, let's just generate a template here, and then have it modify itself to the right code at runtime. So here is the actual code. It's the same thing, except it has dummy values in those positions. And I'll just show you how it works by running it. So first we run this top part. That gets the type. It's this FF87. It matches, so we keep going. Then we load up this value. Then we do our little funky register allocation thing. So now we load the shape, which is 45. and we compare that with this 8f, does not match, so we jump to the C++ function getProp. So getProp does a few things. First, it sort of looks up that shape and finds the property, and then it uses that to patch this code. So it says, okay, the shape's 45, so we'll patch that, and it also knows what these offsets should be, patches those. Finally, it gets the actual value, because of course you need to do that in order to keep running properly, and keeps going. So next time you run, it works pretty much how that code I showed you. So we run the first part, gets this value and type. Then we load up the shape. This time it matches, so we can go on to our fast property access code. We get the slots array, kind of looks like this thing. And then we get to load out the type, and then we load up the value from that. Okay, so that actually worked pretty well. It got it down to 11 instructions. It runs really fast. But JavaScript's a dynamic language, and we want to be able to take advantage of that. So here is the shape of object that we generated a fast path for. But somebody might write a program where they do this, right? Maybe you pass things that have a label foo property as well. And we really do want to make this work correctly and run fast. And it turns out the IC thing really does it. It's almost exactly the same thing. So if you run the code again with this new shape of object, does the first part, gets type and value. So now we get the shape, which is 70. Compare that to 45, and it's not equal. So now we jump to this getProp function again. So getProp, again, is going to look up that shape and find the property. And now it's supposed to patch in the shape and slot offsets. But actually, that wouldn't be a very good idea here, because we could patch it to 70, and then the code would be fast for that new shape, but it's slow for the old shape. So we're kind of stuck, right? We sort of either have to be fast for only one, or else we're constantly patching, and constantly patching is definitely slow. So instead, we're just going to generate a new code for the new shape off to the side. So it looks like this. It's almost exactly the same. Really, the only difference is we're comparing with shape 70 instead of 45. Those offsets, 12 and 8, they could be different if it was in a different position in that object. It happens not to be in this example. And then we just need to patch these jumps a little bit, right? So before, if we didn't match, we jumped straight to getProp. But now we want to jump to this new little fast function here, and then we'll jump back. So at this point, we now have it fast for both shapes, and you can really extend this process indefinitely, right? It can handle prototypes, you can do getters and setters, really anything you want, and just generate as many of these as you need. Okay, so now I just want to show you what a typed compiler can do for this by taking this untyped property access code and just seeing how we can speed it up a little bit. So the first thing to observe is that in these objects, so I put one on here, so it has that prototype shape slots. Sometimes, but not always, the JITs as an optimization will put the value slots right inside the object. So if you do that, you don't really need to load that slots pointer and then load the value. You could just see, oh, actually, they're at these offsets, so we'll just load it that way, and we just eliminated one load. The untyped compiler can't really do that because it has to be really conservative and assume the object could look like anything. The typed compiler gets to wait longer and say, oh, I know exactly what these objects look like before it generates any code. So next, if you look at the bottom here, you'll see that we're loading this type tag, that's what ESI plus 28 is, into EDX. And then what you don't see on this screen is that gets stored to memory, and then it gets reloaded again, and then we test it again. So we're sort of getting this thing just to move it around about 3 times and then test it. The typed compiler could actually see that and optimize it better and say, you know what, we should just test it at the bottom because that's all we really need to do. So that's 2 more instructions out. We freed up our register. So here's a little thing. You don't really need type for this, but it just so happens we generate this move and compare, but you could do that with just 1 instruction, so we'll do that. And then the last thing is to look here at the bottom, right? When we get this node.next value, it goes into ESI. In my example program, that gets stored in node. So again, it sort of gets stored out, and then at the top, we're reloading it just to put it back in ESI. We can say, hey, let's just leave it in ESI. This will work completely. So we move 2 more, freed up register. So here's the theoretical code that we get if we sort of use a typed compiler and optimize it as hard as we can that I reduced from that jam code. Just has 5 instructions. It's really just 2 checks. It says, do we have an object? Does it have this shape? Load the value. So if you compare with C, right, all that C would need to do is the green thing, but it's quite close. So IonMonkey is not at the stage where it can actually compile this code yet. So let's give some props to Crankshaft and show their version of how they did it. So I just tried it out in my program. And you can see that it's actually very much like what I came up with. So at the top here, they have a test to verify it's an object, just like we're doing. theirs looks different because instead of using sort of separate type and value areas, they just put the last bit of the object, they just set it to 1. That's how they say it's an object. So, and then they check the shape. It's actually very similar to ours. You can see that they're just loading a value and comparing that with some shape. In their case, they have to have this little -1 there because their object pointer has that extra 1 from the tag, otherwise the same. And then they just load a field out, so it looks exactly like that. All right, so here's the performance that you get when you use all these things. In a classic interpreter, SpiderMonkey, if I search a linked list with 1 million elements like this, it takes 100 milliseconds. So if we use an untyped compiler with the ICs, we get like a 3 or 4x speed up down to 29. That's JagerMonkey. And if you use a typed compiler like Crankshaft, I found that you are actually almost within 1.5x of C, but definitely within 2x, very, very close. And that's even the highly optimized C. So last things are like, yes, we actually can run JavaScript within 2 to 3x of C sometimes now. And in fact, with floating point things, because we don't have that semantic gap, we found programs where it runs just as fast in JS as C. And we really would like to keep getting faster and faster. And there's a bunch of stuff we can do. But to really get there, we need to bridge this semantic gap, where sort of the processor has one semantics, JS has some others which are different. And sort of, if we could nudge either one a little bit close together, we might be able to get there. So, thank you.
Awesome. Any questions? Oh, yeah. Eric.
So for the untyped compiler, when you're checking the shape and it doesn't match, you're doing a jump to the stub. How does it know where it was called from, the stub? There's a J and E.
So there's actually several different ways of doing that. Do you remember which way we're doing it right now?
The jump actually goes to a little path that bakes in all the information you need to patch the code.
All right, another question over there.
How do you handle the cache invalidation? Like you made an inline cache for all the structure of the objects, or the shapes better, and people change the upper side, like the prototype. And how this invalidation of caching works?
So there's actually, the full answer to that question is kind of complicated, but the example that you gave doesn't really require the invalidation of the cache. So if you change the prototype of an object, that will change its shape. So the next time you have that code, maybe it's now shape 46 because you changed the prototype, so it doesn't run. But there are cases where you have to do that because if you do a GC, garbage collection, then often that will sort of clean up a bunch of old shapes and it might change shape IDs and things like that. So on certain events like that, you actually do have to go through and basically purge all the inline caches and reset them to the original state. So, and it turns out that doesn't really bother performance too much because they kind of, get turned back on pretty quickly.
You mentioned that you would like to see the instruction set for CPUs or JavaScript align up so where you could optimize things better. What would you like to have included in JavaScript, the language, to help you achieve better speeds?
Well, I guess I don't really want to make specific suggestions because I think that should be up to people that are sort of really language designers. It's kind of more like hinting at what we do need. So I think typed arrays help, and the binary data API that's coming in ES6, if you're familiar with that one. So with typed arrays, you can actually create an object where you say, this is an array of doubles, for example. And that means you can get a lot better storage because you don't have to store all these type tags and things. You really just store the numbers. When you read them out, you know exactly what you get. Things like that. So otherwise, I think, and so that basically gives you something like C arrays. The binary data API gives you something like C structs, so you can be fast that way. The main thing is integers, right? That's sort of the hard one. And I could imagine different things, like if there was even just a little dynamic type, like new int32 or something like that in JavaScript, like that would work. There's other ways of doing it too. You could imagine creating a library that just has integer math functions in it, teach the JITs how to see those. But it's really all just about, I guess, some way to express, I want integer semantics now, and then you can compile it exactly to integer math on the processor and be fully fast. So that's pretty much what you need.
Another question? All right, let's give these guys another round of applause for making JavaScript fast so we don't have to.